This is section 3.4 called linear programming. This is not something you would have done in Algebra 1. It's probably not something you would have done in any other class before. So you might want to pay attention, watch the video a couple times, just so that you kind of get an idea of what's going on. With linear programming, basically what it is we take all of Chapter 3, everything you learned in Chapter 3, solving equations, solving systems of inequalities, everything that we've covered so far, we take all of it and we put it together into one problem. So each individual problem takes a long time to do because there's a lot of work involved in each problem. Homework 34 through 40. Some vocabulary, something that you would not have heard before. A solution of a system of linear inequalities is an ordered pair that is a solution of each inequality in the system. Actually, we talked about that one before. But feasible region, you would not have heard of before. The graph of the system of constraints in linear programming is called the feasible region. Linear programming is the process of optimizing a linear objective function subject to a system of linear inequalities, and those linear inequalities are called constraints. So let's suppose we want to solve a linear programming problem. Now the directions say find the minimum and maximum value of the function p equals 2x plus 3y, subject to the following constraints. In linear programming, constraints, when they use the word constraints, they're talking about inequalities, okay, a system of inequalities. In a linear programming problem, the maximum or minimum always occurs at one of the vertices. Vertices are corners of the feasible region. Remember, the feasible region is the graph of the constraints or the graph of the inequalities. Okay? So, when we're trying to find the minimum or the maximum, we only have to look at the vertices. That's a whole lot less points to have to look at because most problems have 3, 4, 5 vertices that we have to look at. But the problem is actually finding the vertices. That can be kind of tricky. So the first thing you have to do is graph the feasible region. So use the constraints. That's the system of inequalities. So if you look here, x is greater than or equal to 0. This is going to be a vertical line, okay, at 0, vertical line at 0. So here is my x greater than or equal to 0. You would shade it, so that would be shading to the right. Y has to be greater than or equal to 2. That would be a horizontal line at 2. So here is my horizontal line at 2, greater than or equal to, so I would shade up. Remember, with the shading, we only look at the overlap. Okay, so I'm not going to shade over here because there wasn't shading there already. And then the last one, x plus y is less than or equal to 7. You do your t-chart, you plug in 0. You get y equals 7, you plug in 0, and you get x equals 7. All right, so we got x equals 7, y equals 0. We've got the 0.07. You connect these. Now, one advantage with linear programming is that they're always going to be less than or equal to or greater than or equal to. We don't have to worry about the less than where we have to do the dotted line. We don't have to worry about the greater than where we have to worry about the dotted line. They're always going to be solid lines, so that's helpful. One advantage. There are lots of disadvantages, but one advantage. So when you do your test point and you plug in 0, 0, 0 is less than 7, that's true. So you shade in the direction of the point 0, 0. So you end up with this shaded region right here. Now the shaded region, this part, this little triangle here, is called a feasible region. We only are concerned with the corners or the vertices of the feasible region. Now if I have 3 sides, that means I'm going to have 3 vertices. Okay, so I only have to look at this point, and that point. That's all I have to worry about, those 3 points. Now to actually figure out what those points are, no, you cannot just look at the graph and say, aha, I know what the point is. Okay, you have to figure out where 2 lines cross. Well, figuring out where 2 lines cross, that is solving systems of equations, which we did in section 3.2. So if you don't remember how to do solving systems of equations, look at your notes for 3.2. Okay, so the graphing part of it was 3.3. But to figure out where these 2 lines cross, we did that in 3.1 and we did that in 3.2. Okay, so this line right here is the line y equals 2. Now, I realize it's an inequality, but when we're doing finding these points, we're gonna use equals. And this line was the line x plus y equals 7. So we have to solve this system. We have to figure out where these 2 lines cross. That's solving the system. You can either do it by substitution or you can do it by linear combination. I would do substitution because I have y equals 2, substitute 2. So you have x plus 2 is equal to 7. And you get x is equal to 5. So this point right here, I know my y value is 2 and my x value is 5. So my x value is 5, my y value is 2. You have to do that for every point, every vertex. Okay? So this one, this was where x equals 0 crossed with y equals 2. Well, this one's easy because x has to equal 0 and y has to equal 2. That's the point 0, 2. Last point is right here. We're trying to figure out where x equals 0 crosses with x plus y equals 7. Well, you're going to use substitution. X is equal to 0. You're going to substitute it in for x. 0 plus 7 equals, 0 plus y equals 7. Or y equals 7. So these 2 lines cross at the point 0, 7. 0, 7, 0, 2, and 5, 2. That's the 2 points, or 3 points, where those lines all cross. Okay? So 0, 2, 5, 2, and 0, 7. And we're not done. See how long these problems are? We're not done. So once we find our vertices, we're going to take our vertices and we're going to plug them into our objective function. Okay? They gave us the objective function at the beginning. Sometimes you have to actually come up with the objective function yourself, but in this problem that was given to us. So I have an x value of 0, I have a y value of 7. I'm going to plug that in. X is 0, y is 7, and see what I get. So 2 times 0, right here, 3 times 7, 2 times 0 is 0, 3 times 7 is 21. If I add 0 and 21, I get 21. We have to do that for each of the 3 vertices, or every vertex that we get. This problem had 3 vertices, so you got to do that 3 times. You're going to plug in the point 0, 2, so you're going to plug in 0, 2. And when you do that, you get P is equal to 6. And finally, you're going to plug in the 0.52 and get 16. And you're almost done, not quite done yet. So, final answer, we have to actually figure out what our answer is. It asks for the maximum value of the function, maximum value. So we're looking at these numbers right here. Whichever number is the biggest, is 21. That would give us our maximum value of 21. It occurs at the point 0, 7. So x is 0, y is 7. This particular question also asks for the minimum value. In your homework, I believe it's either one or the other. I don't think it asks for both the maximum and the minimum. Usually we just ask for one or the other, but in this case, we wanted both. So the minimum value, now we're looking for the smallest number, which in this case is 6. Minimum value of the function is 6. It occurs at the point when x is equal to 0 and y is equal to 2. Finally done. Okay, so I spent about 10 minutes doing one problem, and yes, they really do take that long. Okay, let's see, I think I'm going to stop here for part 1. We're at 12 minutes, and I don't think I can get the whole problem done in 3 minutes. So I'm going to stop here for part 1. I will do example 1 in part 2 of this video.